Hello everyone and welcome back to the Fundamental Theorem. In this video, we're going to tackle a funny little problem. If we had to stand at 0 on the real number line and try to walk to the number corresponding to the square root of -1, I as we call it, where would we need to go? In other words, where is the imaginary constant located in relation to the real number line? We will begin by discussing the so-called geometric mean. Now, the geometric mean of a bunch of numbers is that geometric, i.e. multiplicative action, which when performed several times recursively will have a certain result. Notice how I interchangeably use notions of numbers and notions of actions. And the reason for this is the conceptualization of multiplication as a scaling action on the number line. Multiplying by some number k will stretch the number line such that the number 1 moves over to the point k units away from 0. Essentially, multiplication is a sort of transformation. The geometric mean of some numbers is that number which scales a number line in such a way that repeated scaling results in the number ones reaching the product of those numbers. So the geometric mean of 3, 4, and 5, for example, is the cube root of their product, which is around 3.915. So scaling the number line 3 times by a factor of 3.915, such that each time you scale the already scaled number line, we find that the number 1 eventually reaches a point 60 units from 0. Sure enough, 3 times 4 times 5 is 60. So how does this link to imaginary numbers? Well, notice how the square root of any number is simply its geometric mean with 1. Multiplying 1 and that number gives that number itself, and the square root of a number is naturally that quantity which when multiplied twice by itself gives the original number. Well, what if we tried this with -1? Well, here things get interesting. The only action which when done twice on itself will take the number 1 to -1 is to actually rotate the number line 90 degrees or -90 degrees for that matter. And hence, the point exactly 1 unit above 0 on the real number line must inevitably be the square root of -1. It is evident then from all of this how the Argand plane or the complex plane follows as a natural consequence of this fascinating property of multiplication. And similar arguments can be made for, say, the square root of -2, the only difference being that the rotation will also need to be accompanied by some sort of scaling. The same principles that we use here can also be applied to locate the nth roots of 1, and the concept of multiplication and scaling even leads to important results like de Moivre's theorem. So finally, the answer to the question that we started off with is simple. I lies 1 unit above 0. Thank you so much for watching this video. Do like, subscribe, and share this video.